So in this example here, this one example about the filters, the first example about the filters. So in this example, determine what type of the filter. That means you need to decide what is the type of this filter based on the information that you have before. I mean, based on the component, based on the cutoff frequency, based on the magnitude of the transfer function at initial condition, I mean at 0 point and at the infinity, and calculate the cutoff frequency here, which is the omega c value. So such example here, I mean, it's not preferable to directly just see it is RC or it's RL, so it's low pass filter. No, it's not like this one. So you need to write the transfer function, and you need to calculate the magnitude of the transfer function at the 0 point and the infinity point, and then you can decide is it low pass or high pass filter. I mean, if it's considered or band pass filter or band stop filter, depends on these features or characteristics. So here we have one input source with a resistor R equal to 200 and inductor L equal to 0.1. So we don't know, is it low pass or high pass? Is it band pass or band stop filter? How we can know these things? By writing the transfer function for this circuit. How to write the transfer function? As we learned before, you need to convert your circuit from the time domain to frequency domain. You need to use some of the methods for circuit analysis, like Ohm's law, voltage divider, current divider, KVL, KCL, whatever is the circuit, I mean the type of the theorem that you are going to apply. Then find a relation between the input and output, because the transfer function for any circuit, either filter or any other circuit or any other systems, it is a relation between input and output. For in this case, for example, if we say what is our transfer function, is it GS or HS, whatever is the value. So here it will be like H of S or H of J omega. It's a related or H of omega is a relation between V out over V in. So it will be like V out over V in. V out of S or V out of omega or V out of J omega, whatever is the value in both cases, or are in the frequency or in the S domain. How we can find this relation? We need to write the equation here for this one node, I mean one loop. So you have one loop, so you can write the equation for this circuit by using, like, we can say like V in plus, I mean V in minus VR minus V out is equal to 0, or V in is equal to VR plus V out. Here of S, of omega, of J omega, whatever is the value, it is the same. So what is the voltage of the resistor here? It is the voltage, is the value of the resistor times the current which go through the resistor. We have here only one current, which is I. It will be I. So if it's an S domain, it will be I S, or frequency domain, it will be I of omega. Okay. So how we can write this one? I mean, we need to substitute for the value for VR by the value of the current times the value, because VR is equal to I times R based on Ohm's law. So it will be like this one. It will be like I, which is 200 I, because we have 200 times I, okay, plus V out. Then this current also is the same as the current goes through the inductor. So since it is the same, I can find the value of the current in terms of the V out. So the value of the current here in terms of the V out, I will equal to V out over LS. LS means 0.1 S or 0.1 J omega. 0.1 J omega. Why 0.1 J omega? Because this L will be changed to LS or changed to 0.1 S in the frequency domain. Okay, so that means I will equal to V out over 0.1 J omega, or it will be like 10 over 10 V out over J omega. So this will be like the value for the current. So just substitute for here, then try to find the relation between the V out and V in. As we can see here, if we want to transform our system from the time domain to frequency domain, The component will be changed. So resistor give you resistor, inductor will give you 0.1 S here, or S equal to 10 or j omega over 10. Okay, it is always the same. Then we need to write the transfer function. So he follows that just directly. They said since we have only one node here, so we have only one current. Since there is no node here, there is no distribution for node, we only have one current. So the current will go to this point. It is the same as the current will out from this point. So the same current. So how we find the current from this point? It will be, if we say this is V out, this point is V out, same like the point here. So V out minus V in over 200. So this is V out, I mean V in minus V out over 200. This is the input current to the node, will equal to the output current from the node. So V in minus V out over 200 will equal to V out over 0.1 x. This is the same like this equation, over V out over 0.1. So here V out over 0.1 s, which is like s over 10. Now just rearrange, become like V in minus V out over 200 equal to this 10 will go up. So it's become 10 V out over S, or S V in minus S V out. That means like cross multiplication here, equal to 200 V out. I want to find the relation between V out over V in. This is represent my transfer function, which is H of omega. Okay. So how to find this one? You just rearrange this equation. Take V out there to the other side. So you have S V out plus 2000 V out. So it's become like S plus 2000 V out. In this case, you have here S V in. So I divided over V in. So I have V out over V in is equal to S over S plus 2000. So this will be our transfer function, or HS or H omega or HJ omega. Okay. So here S equal to S, I mean S over S plus 2000. Now, in order to decide is my filter is low pass, high pass, whatever is the type of this filter, I need to find what is H of 0 magnitude and H of infinity magnitude. That means according to the Laplace transform table last time, when we find the how we find the, I mean the initial condition, how we find the infinite values or infinite term. So here just you need to redo it again. For initial value, which is 0, H of 0 you need to substitute for 0 here. So it's become like 0 over 0 plus 2000. So it gives you 0. So H of 0 is equal to 0. Okay, that means if you have, this is the graph, and H of 0 is 0, that means here there is no value. No value for H of S or H of omega magnitude here. The value is 0. Then I want to find the final value. So HS equal to 1 over S. I just rewrite this one in the form of like we did before when we calculate the final condition or the final values in chapter 4. So you divide over S, this become 1. You divide over S, this become 1, 2000 over S. So it's become 1 over 1 plus 2000 over S. Now substitute for S by infinity. H of infinity is equal to 1 over 1 plus 2000 infinity. So become 1 over 1, so it gives you 1. That means H of the final value here is equal to 1. You have the magnitude of H0 is equal to 0. Magnitude of H of infinity is equal to 1. So which this filter, which type have this characteristic? It is high pass filter. You can refer to this table. High pass filter, H0 is 0, H infinity is equal to 1. So it is a high pass filter. Okay, now we decide it is a high pass filter. He asked also to find the omega C, or the cutoff frequency. So how we can find the cutoff frequency? We need to substitute for the magnitude of HS here by 1 over sec 2 or 0.707, as we said before, which is the half of the power, or half of the maximum power. Okay. So just need to substitute here. This is the function H omega, J omega over, we substitute for each S by J omega. This is j omega become like j omega over j omega plus 2000. Okay, so this is what we have here, j omega over j omega plus 2000. How to find the magnitude? We need to find the magnitude and make it equal to 1 over set 2. So to find the magnitude of this part, the magnitude of j omega here of the numerator is equal to 0 plus omega square set root. So it will be like omega. So it's the same as omega. But here it's omega c. Why? Because I already assumed that the value of h omega c is equal to 1 over set 2. Because I want to find omega c. So in this case, just this value become omega c because I want to make it equivalent to 1 over set 2. And this only occurred when omega is equal to omega c. Okay, I substitute here for omega c. Then this one, if I want to find the magnitude of this complex number, it is 2000 square plus omega square. So 2000 square get me 4 million here. Okay, so plus omega c square or and the square root. All this equivalent to 1 over set 2, which is the value at omega is equal to omega 2. Omega equal to omega c. Now you just you make square root for both sides. So you have omega. You make square for both sides. So this become 1 over 2 here, 1 over 2. Then here this become omega c square, and this one become 4 million plus omega c square. Now you solve this equation to find omega c, and the solution is omega c is equal to 2000 radian per second, and this is the cutoff frequency of the band pass filter. That means your magnitude of your circuit will be like this one. At 2000 go to infinity, there is a frequency here. This is 1, for example, here, or depends on the magnitude, and here is 2000 rad per second. Before 2000 or less than 2000, no signals or no magnitudes. That means it is a high pass filter with a cutoff frequency of omega c. Clear? Is it clear? Any question about example 3? Or you already go for lunch?
Clear, sir.
Okay. Alhamdulillah. Next, for example, for here, it is the same. We have a passive element. We do not have, in this chapter, we are only going to cover passive element, passive filter. We are not going to talk about the active filter, which use the operational amplifier. We're going to talk only about the passive filters. So this is another another example for the passive filter, which consists from passive element, inductor, resistor, and capacitor. There are 3 elements. I told you before, don't decide that is a low pass, high pass, or band pass before you go through the transfer function, the initial condition, the final condition, and so on. Okay, so he said show that the circuit is a low pass filter. He said he already tell you that it is low pass filter, but he want you to prove that is a low pass filter. How you need to prove? You need to show that the h of 0 is equal to 1, the magnitude of h0 is equal to 1, magnitude of h1, h infinity is equal to 0. So in this case will be a low pass filter. How we can prove that one? We need to find the transfer function. What is the transfer function? Relation between the output and the input. So the output here is V out, is across the capacitor, and the input is here, the voltage source, which is Vs. So you need to find the transfer function. As I told you before, you have the option to decide which method you want to do. So for example, you have here with 2 loops, so you may have I1, I2. Then you solve this equation for I1 and I2, you find what is the relation between V out and V. This one is V out because this point is the V out, the same as this point, the same as for the 3 points here, we only have 1 node. So we can rewrite equation based on this method. That directly by using the Ohm's law. The summation of current at first node. So it will be like Vs minus V out over S, okay, plus will equal to V out over 0.25 and V out over 1 over S. It will be like the same here that we have. Okay, so here the first you need to convert Henry to S. This will be the inductor S. 0.25 is become 0.25, nothing changed. 1 farad become 1 over S. Okay, then you write the equation for the current here. So the current go to this point, the input current will go to this point is equal to the output currents. So we have one current input which is V out, V in or Vs minus V out over 1 Henry, which is S already, LS. LS means 1 times S, it's S, okay, will equal to V out over 1 over S plus V out over 1 over 4, okay? So V out over 1 over S, V out over 1 over 4. So the summation of the input current or the input currents will equal to the output currents at a specific node, okay? Then you simplify this one to find the direct relation between the current, the V out and V in. You already have only V out and V in or Vs, so you can find the direct relation to them. So simplify, this 4 go up, this S go up, same. So it's become like 4 V out, S V out. You take V out outside, you still have 4 plus, 4 plus, which one? Okay, we already have this also cross multiplication. So you have 4s, this is 4s, and s times s become s squared. So this is V out. Then you have on that side Vs minus V out because it's multiplied by 1, nothing changed. So Vs minus V out. Simplify this one more. After we move this one to the other side. So we have, we will take V out, then we have 1 here because this is the coefficient of V out is equal to 1. So we have V out S squared plus 4s plus 1, which come from this part. So this will be times V out, this is V in. Our transfer function will become V out over V in. That means V out over this V in equal to 1 over S squared plus 4s plus 1. So this is our transfer function. From this transfer function, if I find the initial condition and the final values, I can understand that our filter is low pass filter. As we can see here, H0 is equal to 1 over 0 plus 4 times 0 plus 4 equal to 1. So H0 is equal to 1. Hs here, I have S squared. I can use the same function, but as I told you before, it's not preferable when you find, chapter 4, when we talk about the final values, it's better to simplify to make it in the form of 1 over S in order to remove the infinite values. So you can have specific value for the final value of limitations. So you can see here, we divide only over S square over S square S square. So this become 1 over S square, this become 4 over S, this become 1. Okay, as you can see here, this 1, 4 over S, 1 over S square. That means we divided by S square for the denominator. Also, we need to divide the numerator by S square. So this is 1 over S square, 1 plus 4 over S plus 1 over S square. We substitute for each S by infinity. So this becomes 0. This becomes 1, this becomes 0, this becomes 0. So we have the value is 0. So magnitude of h of 0 is equal to 1. Magnitude of h of infinity is equal to 0. That means this is the characteristic of our low pass filter. For that, it is a low pass filter. Next, we need to calculate the value of the cutoff frequency here. So by using the same transfer function here, we just need to substitute for hs by j omega, and we need to find or to make equivalent to 1 over set 2, which is the value of magnitude at omega equal to omega c, which is 1 over set 2. Then we solve it for omega c to find the value. As you can see here, this is our transfer function, h omega equal to 1 over 1 minus omega square plus j for omega. We substitute for each s here, this j omega square, and here for j omega, correct? J omega square means j square omega, which will be omega square minus 1. Okay, omega square in negative here, because if you have s square and you substitute for each s by j omega square, it is j square omega square. J square means -1, so it's become like omega square here. 1 minus omega square for j omega. This will be our transfer function in the frequency domain. After that, we need to make the magnitude for this transfer function is equivalent to the magnitude when omega equal to omega c, which is 1 over set 2 or 0.707. Okay, the magnitude of the numerator is 1, same. The magnitude of the denominator here, it's equivalent to the 1 plus, equivalent to the square of both the imaginary part and the real part. The real part is 1 minus omega square, and the imaginary part is 4 omega. So square for omega is 16 omega c square. Square 1 minus omega is 1 minus omega c square all square. So this is like you have in the complex number, you have a plus jb. If you want to find the magnitude, it is a square plus b square or square root. This is for the magnitude. The angle will be tan inverse p over a. Okay, so in this case here we have this real part, this imaginary part after the j, all equivalent to 1 over set 2. We solve this equation here. We have this, we come out with this equation, and we need to solve it for omega c. Okay, the only variable missing here is omega c. I want to find what is the value of omega c. So in this case, we cannot solve it directly. We need to have to apply the formula of negative b plus minus b square minus 4ac to solve the second order equations. Okay, assume x equal to omega c square just to simplification. So your equation become x square plus 14x minus 1. Just we assume for simplification. Later on, we will return it back. Okay, then we solve for x. We find the solution is 0.07 minus 14.07. So since our value here is square, cannot be the -1. So it should be this one. So omega square here, omega c square will equal to 0.071. That means omega c will equal to set of 0.071. So it's equal to 0.266 radian per second. Okay, so this is the solution for our the value of omega c, and this represents the cutoff frequency for our low pass filter. That means the low pass filter will allow frequency from 0 until omega equal to 0.226. More than that one, all frequency will equal to 0, no values. Okay. Hopefully it is clear now, and you understand how we can decide the value for your low pass filter. The transfer function of is this or the type of the filter, and how we can find the transfer function for the filter, how we can find the cutoff frequency for the filters. More one thing in this chapter is how to draw the body plot for the filter circuit, and also how to design your filter. You need to design, that means you need to select the value. If I tell you design a filter, that means you need to calculate the value of the elements, value of R, value of C, value of L, depends on the given information. That means if you have this transfer function, you know that the transfer function represent or magnitude at the initial condition is 0, at the infinity is equal to 1, that means this is the high pass filter. If it's 1 and 0, that means low pass filter, and so on. And you have 4 equations to find the value of omega c and the value of omega naught for the band pass filter and band stop filter. So now, since you already have the transfer function for the filter, it's easy to draw the body plot. Why? Because previously when we start this chapter, we learned how from the transfer function we can draw the body plot. And we said we need to write the transfer function in the standard form. Then we need to identify the different component or element or factors of our transfer function. Is it a gain? Is it a gain? Is it an integral form? Is it derivative form? Is it first order good or first order 0? Then we draw each element individually, depends on magnitude and phase. Then we combine the different factors or different element of our body block into a single graph. Okay, so we have this